practicing what we preach in terms of adopting an experimental approach to collective behavior, the organizing committee decided that we'd like to experiment with crowdsourcing you, the workshop participants, to help guide our open-ended discussion after both of the talks today. So your task is going to be to think up open-ended discussion questions like usual, and then later on vote on other people's questions. So Marina will be collecting possible open discussion questions, and she'll look on either the Zoom chat window here or in Jamboards. Then she'll create one or two Zoom polls to ask you which question you want to hear discussed. And this way we'll hopefully prioritize the issues that you most want to hear about, making it more likely that you will add your own 2 cents. So try to get us your questions before the last minute or two of Charley's talk. And if you want to make sure that Marina picks them up, you can use one of those 2 tags to say that you want this to be a candidate question. Okay, so without further ado, I'd like to introduce our Graesser, and you probably don't know, but we don't do the fancy bio blurbs. We don't want to cut into your time, so just take us away.
Can you see anything now?
That's perfect.
Okay. Okay, so today I'm going to talk about an international assessment of collaborative problem solving. It's actually the first international assessment. And I want to mention that collaborative problem solving is different than collaborative learning or collaborative decision making. It's very visible. If you solve the problem, everybody knows it or not. And so there's a certain accountability in collaborative problem solving. So this is what I'm going to talk about, an assessment of problem solving throughout the world in PISA and PIAC. For those who don't know, I'll define those later. And then I'll talk about collaborative problem solving assessment that occurred in 2015. And then finally, some attempts to automate some of the components for collaborative problem solving training. So let me just briefly mention these international assessments of problem solving. I don't know how many know what OECD is, but it's an organization that primarily out of Europe that tries to assess the economic well-being of countries and what can improve their lot, their economic lot. And a big part of it is education and skill training. And you can kind of see how much a country can advance through that training. And so there's a program for international student assessment that involves 15-year-olds, about 500,000 students throughout the world. And then there's the program for international assessment of adult competencies, which we call PIAC, and that's for people 16 through 65. So I've been involved in the problem solving ones for, about 12 years, starting with the problem solving in technology rich environments and adaptive problem solving that's going on right now. For PISA, there's complex problem solving, and then currently, well, one that I was involved in a lot is this collaborative problem solving. I served as co-chair of that. So there's many countries involved, and here's a map of the world, and you have in the gray the traditional OECD countries that are involved. And then you have a bunch of partner countries, and these are the ones that were involved in the PISA assessment. And then you have others that have been in previous cycles. And one thing I might mention, you have to purchase being part of the assessment. So it's kind of like the customer is the countries. So people try to correlate skills with how solid the economy is in these countries, measured by GDP per hour worked. And here's one interesting one. And if you look at reading skills, the more skills that the more jobs that require reading skills in a country, the better the GDP. And so you could have similar functions for collaborative problem solving, but you'd need some sort of assessment of that. And that's why they commissioned the collaborative problem solving assessment. So there are other OECD reports that occur. In fact, I highly encourage anybody interested in this, just go to OECD.org and you'll see a big library of all these reports. This particular report by Elliott, which I participated in, had the following exercise for a bunch of experts in AI and cognitive science that said, suppose you had to take the test, how well would the computer do on that test? How well would the visual processing pick up, for example, that windmill? How well will modern AI systems and natural language understanding be able to interpret this or interpret the table below? And so you can read that report, and it's interesting, the experts, some were realistic, others were what they called pessimists, and others were optimists. I ended up being a pessimist. They redid collected data again just during the last year, and I graduated to be a realist. So I'm happy to say I'm getting closer to reality. Now, the second report down there, which I'd recommend you downloading and getting, is a recent report that had people analyze skills of humans, what skills, and they had a taxonomy of skills. Various people proposed taxonomies. People in the workforce proposed taxonomies, and people in AI proposed taxonomies. And the big question was, what can the computer do versus humans? And I think this is relevant to some of the discussion that we had last week. Namely, some skills are good for humans to do, others can be done by the computer. And as you know, everybody is fearful of maybe robots and AI taking over the workforce. So asking this question has practical consequences in addition to scientific implications. This is a graph that is highly disseminated now, that was done 2 decades ago. And here you see, if you look at jobs throughout the world, you see that jobs for manual and routine tasks are going way down, whereas collaboration tasks are going way up. And complex non-routine tasks are going way up for needs for jobs. And hence, that's what motivated these people to have an assessment of collaborative problem solving. So let's turn to this, collaborative problem solving. This is the second part. And if you want to read more about the science of collaborative problem solving, I recommend this. These were some of the members who participated in the collaborative problem solving effort with OECD. And if you want to see the results of the PISA for collaborative problem solving, you can download this and off of the OECD website. So it takes a big village to do this. You have all these experts, you know, it's just amazing, dozens. And this doesn't even cover it, because you have an expert in each country who has to approve the assessment. So the country, you can't collect data until you get their approval. And these get translated in many different languages. So in fact, there's more languages than countries actually. And so they have to sign off on it. But it's a very big effort. The other thing I wanted to mention, the questionnaire development there, that's important. That's also assesses for each country. It asks questions not only from the students, in this case by PISA, for PISA, the 15-year-old students, but also parents, teachers, and other stakeholders. So you get some sort of demographic data and self-report data and subjective data from there. So when you talk about collaborative problem solving, there are all sorts of things to consider. And in fact, there is a theoretical framework in the document that talks about what was taken into consideration in trying to understand collaborative problem solving. So you'd want to know what type of collaboration is it? Is it a hidden profile problem where some people know some things, other people may not? Or is it collaborative design? A big issue was interdependency versus independence. And there was primarily problems that required interdependency, where you can't solve the problem alone. No one person can solve it. And so that was a big issue. Another issue was, do you want a static problem that doesn't change throughout the time course? Or would you prefer to have dynamic problems where the problem changes in midstream and you can see how well people have strategy shifts? So we ended up deciding to have more static types, at least for this first assessment that was ever conducted worldwide. And of course, you want to know about communication media. You use chat, spoken, face-to-face. We ended up using computer agents for a variety of reasons I'll briefly mention in a minute. You also asked about team compositions. How many members of the team? It was primarily small teams. As we will see, it's really a group of computer agents with one human. And I'll get to in a minute why we had to do it that way. Another issue is for composition, do you have assigned roles or emergent roles? This is part of the theoretical framework. I'm going to talk a little bit later about emergent roles, where it's just, you're not assigned who's the boss, who's the scribe, but rather it emerges dynamically. An important issue in red down there is looking at the style of the agent. Sometimes some agents were unresponsive, sometimes they were incorrect, disruptive, domineering. So you want to manipulate the nature of the agent, because you don't want to have groupthink where people just want to quickly solve the problem in a very easy way. You want, sometimes there's discord, sometimes people have to fill in for another team member that is not performing very well. So there's a lot of issues in terms of composition. This is the definition of collaborative problem-solving competency. I'm not going to read the whole thing. The two things I want to mention is this is an assessment of collaborative problem-solving competency. It doesn't cover the full theoretical framework. You have to be selective on what parts you want to get out of it. The other thing I wanted to point out is we use these computer agents and that interacted with one human at a time. There was a lot of debate over whether to do this, whether to have human or human versus agent human. And we decided human was not possible, because you have to handle many countries and many languages, and it would take too long to handle and transcribe all that sort of stuff. And you have a time limitation. You have to do it in 1 or 2 years. It's hard, at that point in time, it was hard to schedule students together, networking. And of course, there's control. And this is an important issue. You can manipulate the agents and choreograph them in ways to come up with conditions to allow a good assessment of collaborative problem solving. So this next slide is the kind of assessment grid of what we tried to cover in assessing the skills. You have one dimension along the columns that were used in previous assessments of problem solving, where you talk about exploring and understanding the problem, and then trying to represent it and formulate it in some way that you can act on it. There's planning and execution where you're actually doing something to solve the problem, and then monitoring and reflecting. So that you have that kind of problem solving axis, and that's crossed with the collaboration one, where the first is establishing and maintaining shared understanding, and that includes people's different perspectives. So you try to get the different perspectives on the table. And then the second part is actually taking the appropriate actions to move forward. And finally, establishing the organization of the team and reflecting on that. So if you cross the 4 problem solving components with the 3 collaboration components, you get these 12 cells. And what you do is create problems and scenarios that come up in kind of stage assessments that populate these 12 cells, and that sort of thing. So here's an example of one of the problems. And again, this is for 15-year-olds. The goal here is you have people from out of the country visiting your high school, and you want to, come up with a schedule on how to handle the visitors. And so you can, for example, take them to a museum or a community market or an electric car factory, and you have to make a decision because they can't do all of them. And so these are the participants, you, the human, versus George, Rachel, and Brad. They are all agents, okay? And then you have chat here. So you have the chat in getting started. And then this is important. You have points, kind of multiple choice points, and this is where you get the assessment. So they click on this. There is no natural language input on this because, how are you going to translate natural language in 100 different languages? That's impossible. So it's all click and drag and drop and actions. And it's usually a limited number of alternatives, like 3 to 6. So you can do standard psychometrics on that. In psychometric item response theory is very typical in that field. And then you can have a notepad for notes on there. And then down there this apparently is in that B1 cell, building a shared representation and negotiating the meaning of a problem, common ground. Okay, so these problems are pretty complex. I mean, you have the 4 agents, you have to consider time, you have to monitor the time, fill up the schedule in a sensible way. There are 3 different locations. You have to manage the transportation. And of course, there's also sorts of notes on constraints. And again, at each point, you have this multiple choice that you choose, and that's where you get the assessment. So there's about 100 assessment units among 5 problem scenarios, and Each scenario takes 10 to 20 minutes. And again, you have observations that populate those 12 cells in the matrix. So here's 4 levels of proficiency. And this is greatly simplified. If you actually go to the report, these levels are elaborated in fine detail, but you have a not proficient level where low proficiency is, they can only handle simple problems and very little collaboration. They don't initiate anything. You have the medium problem complexity. In the high end, you see there's high problem complexity and the collaboration demands in overcoming obstacles, disagreements, and conflict, where sometimes you can make decisions to take a leadership role. Okay, so here is the assessment. This is the sort of data you get, and they have the different kind of the countries listed from the best. Apparently it was Singapore, and the worst was Tunisia. In truth, they're not big on wanting to do a lot of comparison of countries. Rather, the goal is to have this test repeatedly to help each country on its own trajectory. However, that doesn't stop them from wanting to go this route. So here's, you see Germany and the United States is a little bit above average on this. Interestingly, you can compare girls versus boys, and in all countries, all of the countries, girls outperformed males in collaborative problem solving, which is kind of an interesting observation. If you compare collaborative problem solving with individual problem solving that was conducted earlier, males have a slight advantage over females, but you need a real magnifying glass. It's a near tie. But there's something about collaborative problem solving that females excel in. You can also see what activities lead to better performance. And what you find is these experiences in schools like band and orchestra and yearbook editing and volunteering service and sports, that leads to better collaborative problem solving. That's correlated and predictive of these scores. Okay, so there's an approach, there's some challenges on what to do with these data. First, collaborative problem solving is not part of the curriculum. Might you want to have collaborative problem solving as part of the curriculum? And do you want it to cut across areas, whether it's math or science or not? So that raised a bunch of issues. The other thing is you're really starting from ground zero because most teachers don't know how to teach collaborative problem solving, and students aren't particularly good at it. And that's where they say technology needs to play a role in training. And so it's a big goal right now of wanting to do. So let me shift to the third and final part, namely attempts to automate some of the components so you can train them for collaborative problem solving. And so this is one system that came out of Iowa State University with Steve Gilbert. And this is where you build an intelligent tutoring system for training these skills. So you have human learners, and then you track their interaction, and then you have these team agents that can come in and swoop in order to provide some training at the right time. So, so what might the agent do? In a project I had with David Schaefer at University of Wisconsin a few years ago, we talked about just coming up with simple rules that get activated. So you look over the exchange, and then you have these rules to have an auto mentor agent come in. So the first one is if the team is stuck and nobody doing anything, then you say, what's the goal here? Let's get back on track. Or you can say if the team member meanders from topic to topic, then the agent might say, well, I'm lost. What are we doing now? So you can come up with these simple rules as you look over the exchange. And that's kind of this is kind of really an example approach of what you might do in building an intelligent trainer. The last thing I want to say is one of my, well, almost last, one of my doctoral students, Nia Dowell, who's now at UC Irvine, actually had an automated way of covering the natural language in chat sessions and try to identify different social roles. And she did this by looking at the natural language and tracking participation, internal cohesion, namely if there's a student basically saying the same thing or elaborate what they already know, versus responsiveness versus social impact. If they say things, do other participants do uptake and follow through? And how much new information is there? And so we have a method, and how dense is it? So there's automated measures. And what she does is using clustering analysis to try to classify them into different categories. And these are the categories she identified, whether it's a follower or socially detached or a leader. And so you can use these automated ways and looking at the roles, and you can imagine these rule-based systems kind of going in there. And if there's a problem, you can come up with these speech acts by an agent to help improve the lot. So this is my last slide. Educational Testing Service has built this EPCAL system, which tracks the face and the chat and the interaction of people. And what they're doing is trying to track collaborative problem solving over time, and then see how successful it is and do the standard sort of data mining and machine learning to discover patterns. I guess there's a lot of research now on comparing human-human interaction versus human-computer agents, and a lot of interesting work in that's been evolving. And finally, I want to mention that one of my doctoral students now at University of Colorado, Sidney DeMello, received one of these big National Science Foundation trying to get an AI Institute for student AI teaming. And so I encourage everybody to go to that because it seems highly relevant to this workshop that you so nicely developed. So with that, that's what I have to say about collaborative problem solving.
Great.
Yeah.
Thank you very much, Art. Behind the scenes, we've already been voting on who gets to ask questions. That was truly self-organized on Suparna's part. So I'm seeing maybe Mark and then Charley, and then maybe we should go on to Charley's talk.
Yeah, okay.
Well, Art, excellent talk. You can hear me?
Yes. Mm-hmm.
Yeah, so I understand the rationale for having these agents, artificial agents in your setup.
Mm-hmm.
I assume you don't use deception, right? Do people know that they're dealing with artificial agents? And does that framing, does that matter whether you're told that you're dealing with bots versus other humans on your team?
Mm-hmm. They are told for the international assessment that they are agents. However, in the work with by Steve Gilbert, where you plant an agent as a peer or a mentor, he usually informs them that they are an agent. However, they have done small scale studies and a couple of others not telling them. And but there's an ethical concern, as you might imagine. So I think that's one of the interesting issues for the future, is to compare whether they're knowingly interacting with agents versus people behind the curtain. I think that's a very interesting question for the future. I haven't conducted any studies that manipulated that. Yeah.
Yeah, I was wondering what types of errors people make in performing this task, because it seems far from kind of a binary correct versus incorrect, right?
Right.
And
Yeah.
kind of the second part of this is that could some of these errors be due to kind of different expectations about how the other people will behave, right? Where if you have like a different expectation than it's kind of in the simulation or in these scenarios, then if a misalignment there, then what you're doing could be rational in your kind of local community, but generate an incorrect answer on the test.
I'm glad you asked that question, because we wanted to see the distractors. We wanted to get the distractor data, the people on the team, but ETS at the time said no, they couldn't afford to provide the distractor data. And that disappointed a lot of us. But one related issue is the distractor by being polite. There are some countries that people are reluctant to ask questions of another person, and we worried a lot about that. So cultural differences we could learn more about that if we could see the distractor data. Yep. Yep.
Great. And so while you're there, Charley, we can begin to transition to your talk after Art's great talk. So take us away. Yes,
Great.
It is working.
Yeah. Can you guys see my screen? Okay, let me just adjust the video so I can see you guys all. So feel free to turn your camera on if you'd like to. So today I'll be talking about some work using visual attention to model social influence in an immersive collective foraging task. So a lot of my work has studied human learning, and a lot of cognitive science research on human learning has really focused on these tasks where individuals interact with a set of stimuli, either in the lab or online, but in these settings of imposed isolation. Whereas in contrast, the majority of our interactions with the real world are actually in social contexts, where our actions influence and are in turn influenced by other people. So what I've been trying to do is understand the mechanisms behind social learning and how that interacts with what we understand about individual learning. Now, one type of framework for studying social learning is to cast it as a collective search problem, where a variety of real-world tasks, such as developing new technologies, trading on the stock market, or figuring out what are interesting scientific research problems, can be framed as a search problem in some sort of fitness landscape, where the kind of the specifications of your technology, your stock portfolio, or the parameters of your research question correspond to some kind of outcome, some sort of fitness value, where we typically have two different streams for learning, either through individual innovation, through individual trial and error, or through social imitation, seeing what other people are doing and trying to use that social information to inform how we should behave. In animal research, a very similar type of problem is studied using what's called the producer-scrounger game, which is a type of evolutionary game theory dilemma. And a scrounger, for those of you not familiar, is someone who kind of borrows or lives off of others. So here's what this task sometimes looks like in an experiment with birds, where they've hidden food pellets in these different wells here, these different patches. And so using the producer strategy is to use individual learning to kind of look out and investigate the different wells to see if you can find a reward patch, while playing the scrounger strategy is to use social imitation to copy other successful foragers. And here you see a setting where someone's found a patch and there's a lot of scroungers who've kind of congregated around here. Now, in both of these types of collective learning problems, either on a fitness landscape or in producer-scrounger games, one of the main dilemmas is to figure out whether to imitate or to innovate. And this dilemma is well illustrated in what's known as Rogers' paradox, where we can imagine this very simple case where let's assume that individual learners have some sort of fixed fitness, so this red line here, But then in the simplest case, we can describe the fitness of social learners as being dependent on a number of other social learners in the population, as frequency dependent fitness. So if you're the only social learner in the population, that's great. There's plenty of people to copy from. But if everyone else is a social learner, then there's no one finding new patches or coming up with new innovations. Rather, we're stuck in this information cascade, which leads to a collapse in the overall fitness of the population. So successful groups need to balance individual and social learning. This is not a collaborative problem-solving task like Art was talking about, but rather this is everyone's trying to maximize their own rewards, but your own behavior has this kind of dynamic trade-offs with the environment, has the dynamic trade-offs based on how many other people play a specific strategy, right? And so what I'm trying to answer here is, how do collectives achieve this balance and how they adapt it to different types of learning environments? Sorry, usually in the settings, people find some intermediate balance. This is the evolutionary stable strategy from Rogers paradox. And I want to understand how people reach this balance and what this looks like. So my work is quite inspired by previous work on collective search in virtual environments by people such as Rob, Peake's Craft, where people are controlling the different avatars in these 2D environments to acquire rewards. But what we've done is created a task, a collective foraging task in the game Minecraft, where we make use of this kind of realistic and naturalistic setting, where this you have a limited field of view, which creates attentional trade-offs and opportunity costs for social learning. So you can either focus on individual search, or you can look at other players to perform social imitation. But the kind of naturalistic constraints of the task mean that focusing on individual search sometimes comes at the cost of social learning, and looking around at what other people are doing sometimes comes at the cost of foraging yourself. And we get these really rich and dynamic social interactions through spatial positioning and visual gaze data. So the task starts off with an interactive tutorial. Sorry if it's in German, but actually I think people like Rob actually speaks pretty good German from my experience. People are taught kind of how to play this game. They're taught that you can smash blocks by clicking and holding the mouse. It takes about 2.25 seconds to destroy a block. So it's costly to forge. And they're taught that blocks either contain a reward, which is indicated by a blue splash, which is visible to other players as well. Or other blocks have no rewards. So there's no, I'll kind of fast forward through this a little bit. So participants are incentivized to collect as many rewards as possible in these 2-minute rounds, where they're in 2 different types of reward environments. Some reward environments are smooth, and these kind of paintings in the game illustrate kind of the top-down perspective of how the reward distribution is so like. So the black pixels correspond to rewards. So they're in these clusters. And what this means is that when you find a reward, there's other rewards going to be nearby. But this also means that in a collective search context, when you see someone else find a reward, that also is an indication that there's other rewards nearby, that you can use this social information. And in contrast, in these random environments, there's no predictability of rewards. And we map these either to watermelon or pumpkin blocks, and we counterbalance this across groups. So participants perform 16 rounds of this task in a 2x2 design. So they're either searching smooth or random environments, and they're either doing this alone or in groups of 4. And so we use these solo conditions to kind of provide a nice baseline for how individual search works in these 2 different tasks, 2 different reward environments. I previously presented a really early version of this task using a really small sample of n equals 44 participants. We had to stop data collection due to the outbreak of COVID. And what we've done now is we've collected, we made some minor tweaks to the task, and we've collected a full n equals 128 sample. So this is what we're focusing on today. And we made the kind of minor tweaks we've made are that we've removed this persistent reward information. So you see these blue blocks on the original version that kind of were persistent, but here means that social information is more fleeting. So you really have to be looking around or you miss it. We've added randomized name tags above individuals to allow for selectivity in social learning. So you don't have to use it, but if you want to specifically follow, copy some specific individual, you now can. And we simplified the reward animation as well. So we have 2 main hypotheses in going into this. The first one is that participants will adapt to social learning depending on whether social information is useful. So the smooth environments mean that rewards observations predict other reward observations nearby, so you can use social information. compared to the random environments where there's no real use to it. But what we want to understand still is that how much do people adapt and what biases are still persistent. The second hypothesis is that we expect people will achieve some intermediate balance of individual and social learning. This is kind of the outcome of Rogers' paradox. But it was unclear how people achieve this balance and what this balance exactly looks like. So I'll start with some behavior results, where first I'm going to look at performance and search patterns. So we find that the reward structures influence both performance and foraging patterns. So here I'm just showing the average reward in the 2x2 conditions. And we find that there's higher reward in smooth environments in both group and solo. And here reporting the fixed effect of a Bayesian hierarchical regression. And what we find is that when we control for reward depletion, since there's a limited number of rewards and there's more people searching for the same amount of rewards in the group environments, when we kind of normalize for this, we find there's no difference between solo and group, right? So people are performing better in smooth environments, but they're not necessarily performing any different between solo and group. Now, these reward structures also influence foraging patterns quite a bit. So participants actively avoid each other in these random environments. So there's been a pairwise distance between individuals. So see this has much higher in the random environments than in the smooth environments. And we see that there's even more avoidance of one another in the group environments than in solo. So the solo rounds are searching on separate environments, but we can still compute pairwise distance as if they were on the same environment. So this kind of has a nice baseline because they're still using the same reward distributions, right? And even though they're on separate environments. So this is kind of a nice baseline. Yeah. And in the random environments, you also see that there's faster foraging. The foraging rate is much faster, destroying more blocks. Whereas in the smooth environments, they're being more selective because there's a reward structure there. But in this group rounds, we see that the selectivity is amplified even further. Now, the second analysis I want to show you is based on this automated transcription of the visual field, which I think is something we really need for this task. So here's just a very simple screen recording of the task. And what we've done is we've able to simulate the whole state of the world from each person's perspective using this Unity game engine. We've mapped each unique entity, each player, each block, each reward observation to a unique RGB value. So here I've overlaid the two to show you that we have a high fidelity of the simulations. And the purpose of this is that we can read out all the pixels from every kind of screen at every point in time and detect what is visible at any point in time, which players are visible to which players at any point in time, which rewards are visible at any point in time. And so we can construct things like a visibility network, which captures this asymmetric visual attention between individuals, right? So we have these weighted edges and they're directed edges, and the edge weights correspond to how much time an individual sees another, right? You see interesting asymmetries in this. So I want to first look at just visual attention. So how much people were looking at other people in general. So kind of the average number of visible peers at a given point in time, right? So the more peers are visible, the higher this is. The more time you spend looking at other people, the higher this value is. And we see that there's increased social attention in these smooth environments. And again, this is the fixed effects of the hierarchical regression. This increase in tension in smooth environments comes at a cost though. It means that they destroy fewer blocks, right? So they become more selective and they destroy fewer blocks. Yet, this increase in tension and selectivity made no difference in terms of reward rates. So they're being more selective when they're looking at other people. So our kind of trade-off worked out in this task, but they're not finding any few rewards. They're being more selective, but it's paying off. It's not benefiting them necessarily, but they're breaking even, right, in terms of how they use social information. Now, we also find that when we construct these visibility graphs, we can compute the in degree and the out degree of these graphs. And here I'm plotting them against one another. We can think about the in degree as something like the celebrity factor, how much other people look at them. We can think about the out degree as a paparazzi factor, how much you're looking at other people. And we see that there's general asymmetries, right? So quite weak though in the random environment, but they become much stronger in these smooth environments where social learning has traction. So we see increased asymmetries in social learning, right? These people down here are celebrities, they're being looked at a lot, but they're not looking at other people. And vice versa, we have on the other edge of the spectrum, these people who are spending a lot of time looking at other people. They're using a lot more social learning, but themselves are not using much, the target of social learning. And this also suggests that this kind of balance between individual and social learning is not necessarily a homogeneous kind of mix that we see from Rogers' paradox, but rather we see heterogeneity in individuals. Now, I want to talk about a third analysis based on the spatial trajectories that we have, where we can do interesting things of looking at the dyadic distance between individuals, how this changes over time. And we can look at build these proximity networks, where these undirected edges are weighted based on the average pairwise distance between individuals. Now, we so far we only looked at social attention, right? But now we wanted to kind of move towards social influence. And one method for doing this is to extract pull events from movement patterns. And this is inspired by methods used to study wild baboons, the foraging behavior of wild baboons with geo-tracking collars. And so what we do is you look for candidate pull events from min, max, min sequences in the pairwise distance between players. They're close together, they're far apart, and they're close together again. And we detect these events based on filtering these candidates based on a number of criteria. First of all, we filter based on strength. The change in distance relative to the absolute distance should be large. So it's not just a wiggle at a distance, but it's a meaningful change in distance. We filter by disparity, such that one player moves more in the first segment, but then less in the other. And leadership, that one player consistently moves more in the first segment and less in the second. So I think I didn't explain this properly here, but I think you get the idea. And so here's an example of illustrative pull, where we have the leader colored in orange and the follower colored in pink. The numbers here correspond to time point 1, 2, and 3 from these vertical dashed lines. These gray and blue squares correspond to the rewards that have been observed in this round. So what we see is that time point 1 to 2, the leader moves from this one patch here to this other patch over here, whereas the follower tries to explore this bottom right-hand corner, doesn't find anything, turns around, sees the leader here, and then moves in to imitate. And in time 3, they're both foraging from the same patch. So this is an example where the pink player has been pulled in by the orange player. And we can look at the frequency of these pull events, where we are able to get a nice benchmark from these solo rounds. Like I mentioned before, they're searching on different environments, but we can use the same, essentially assume that they're on the same coordinate system and try to see if we can detect these false pulls in the solo rounds, which would be due to the reward structure, right? And so we kind of see that there are sometimes pull events in both random and smooth. We have a slightly higher, more false pulls in random because there's a correlated reward structure. But as a benchmark, we can compare these to the group rounds, and we see there's far more pulls in the smooth environments, right? Comparing group to solo, and there's actually fewer pull events in the group environments for random, right? So this makes sense because you want to be influenced by the people, you want to be pulled by people in the smooth environments, but not in the random environments. And we can also model this using a Poisson regression. We're modeling the incidence rate of pull events, and while the group rounds have a reduction in the rate of pull events, we see a much higher incidence of pulls with smooth group. We can also relate leadership, kind of being the leader in these pull events, to social attention and spatial proximity. So remember that these pull events were only computed from spatial trajectories, but they also relate to visibility. The leadership value, which is the number of times you are a leader minus the number of times you're a follower, is quite well correlated with in degree and out degree, right? So leaders have high in degree, they're being looked at. Leaders have low out degree, they're not looking that much at other people. And it's also based on the difference between in and out degree. So leaders are much more individual learners than social learners. And we also find leaders tend to be at the outskirts of the group, kind of expanding the frontier. And we can kind of model this using the eigencentrality from these spatial proximity networks. So the more central, the higher eigencentrality you have, the more central you are in the group, right? And so we find the leaders actually typically have lower eigencentrality. And again, these are the fixed effects of the Bayesian regression, where we're controlling for individuals and groups as random effects. So these are all reliable effects. But even more interesting than this, I think, is that social attention and leadership are not really well related to score, right? We have consistent in degree and out degree within individuals. I'm not showing the results here, but I can show that afterwards if anyone's interested. But in degree and out degree don't predict overall score. So here's your in degree, here's your out degree. It's not related to score. We can put this to regression. It's also not related. And also leadership is not related to score, right? You're not performing better. So here's comparing individual to your group score, but we can also do this for overall score in general. I mean, also not finding no effects. However, leaders have higher instantaneous reward rates during the poll events. So if in general, leaders not performing better, being more of a paparazzi versus a celebrity is not making perform any better. But people are still selected because the people being copied, the people being followed, right, these leaders, they're having higher reward rates during poll events. And we see how this, so we're modeling this with the Poisson regression again. We see a higher incidence rate of rewards for the leaders in this time period, their followers. So quick behavioral summary. We see that social learning mechanisms adapted to the environment. Participants attended more to other players in smooth environments, even at the cost of having less time to destroy blocks. Yet this slower foraging rate didn't really impact performance. Social attention was also directed asymmetrically with increased specialization in these smooth environments. Yet beyond only attending more to others, participants were also influenced more by others in smooth environments, producing more poll events. And while the social learning strategies among individuals were quite consistent, so heterogeneous but consistent, this seemed unrelated to overall performance, right? Yet leaders had higher reward rates during poll events, suggesting some success bias activity in social learning and how people are influenced by one another. So now I'm going to move on to the computational models that we developed to try to model this task. And so what we're trying to do here is we're trying to sequentially predict which block a participant will destroy at some time t. So we have kind of turned this into a discrete block prediction task. And the probability of destroying some block is computed based on a softmax over a set of features times weights. So every block has some feature value, and then we estimate some weights. There are different models consider different features, which capture hypotheses about individual and social learning mechanisms. And these model weights are estimated using hierarchical Bayesian methods and STAN with individual and group as random effects. So I'm going to start with this kind of snapshot of the task. So the overall round is 2 minutes. So this is kind of partway through. These trajectories show you from where they started to where they currently are. So the head of the player corresponds to where they currently are at the point in time. And this is the state of the world. The green blocks correspond to undestroyed blocks. Blue are rewards and white are no rewards. And we have these 4 different players. I'm going to focus on player 2 in purple here. So the first set of feature we can produce is purely based on locality, right? We would expect that people will prefer to destroy blocks close to them, right? So this is a feature map purely based on locality, based on spatial distance. Now, second feature map is based on Gaussian process reward prediction. So this is a method I've used in a variety of other papers before. I won't go into too much detail here, but essentially it's based on the rewards that you've seen, which other blocks are likely to also produce rewards. And so this is essentially just a Bayesian Gaussian process model here, where we slap on a sigmoid transformation to turn it into a binary classifier. So typically this is trying to produce some continuous reward value. Here we are predicting the probability of reward. But we can essentially, here I'm just showing you this latent variable, where the higher this latent variable is, the higher the probability of reward. And so based on the reward observations that individual has seen, so we're using visual visibility data here, we're able to predict which other blocks are likely to produce reward given the generative structure of the task. So these are the individual, the first 2 rows here. This row here are the individual features. We also have some social features as well. And these social features are based on this kind of transcription, visual transcription data, where we first classify individuals as either being visible or not visible. So we only consider individuals who are visible. And then we classify them as either being observed, being successful, or not observed, being successful. So we call that unsuccessful. And so then we can construct these proximity maps. So again, the kind of distance-based map, where with respect to all the successful players, so average across all the successful players, and unsuccessful player map, average across all the unsuccessful players. We then combine these together with model weights to then make some model predictions. And so the higher these values are, the higher the probability the model thinks they're going to make a choice. And this red X corresponds to the choice that the purple player actually made in this trial. So here I'm going to show you these early model results, and these are the group level posterior weight estimates. And so we start off with some kind of basic sanity checks that locality matters in all conditions. People prefer choices closer to themselves. And we also find that these GPU predictions work best in smooth environments in which they're aligned, whereas the random environments, they simply are not predicted, right? So in all these cases, we see much stronger weights for the GPU predictions for the smooth environments than random. Now, the social features I think I want to focus on is that here we see that there's, in both random and smooth environments, that there's a similar influence of successful players, right? When they're seeing someone else being successful, they're more likely to move towards them. And this is the case even in random environments, which is quite surprising. Recall that there's no reward structure. So seeing someone else be successful should not actually make you move towards them, but nevertheless we see this. But rather where we see adaptation is the avoidance of unsuccessful players, where we see increased avoidance of unsuccessful players in random environments. So we're only getting started with the modeling. So we have a couple of other alternative models that we either run or currently are running. So one that we've done is where we just have no social information, and we generally have worse fits, but the individual weight estimates, the features for the individual weights stay the same. Sorry, the weights for the individual features stay the same. We're currently running a different model that has a single weight for social proximity across all players. So no differentiation between successful and not so successful players. And we expect this to be a worse model because we see that there's kind of strong selectivity between moving towards successful players and moving away from unsuccessful. And we're also going to try one more model where we have a unique proximity weight for every individual player. And we can try to look at how much selectivity there is at the player level. And one idea for this is we then relate the selectivity to leadership or in and out degrees of those players to try to look at how much, if you can really understand the selectivity beyond just success or but also based on learning strategies of individuals, right? We're seeing this kind of asymmetry of social learners copying individual learners. Can we also see this activity in these model weights? And lastly, we're also planning on running some agent-based simulations. So the Minecraft experiment is already kind of a bit of a simplification of the real world, but for this agent-based framework, we've simplified it even further to a 2D version of this task, where we can try out different model weights, like hypothetical model weights, to simulate behavior. We're essentially defining destinations for each individual agent, and we're letting the simulations roll out. And we can look at what would a homogeneous balance between social and individual learning look like versus the heterogeneous specialization outcome that we observed in this task. And how would alternative selectivity biases change both individual and group performance? So that's an analysis that we haven't run yet, but we hope to do this after we feel satisfied with the model results. So in summary, we find that social learning adapts to the demands of the environment. We see more social attention and more social influence events in smooth environments where social information is actionable. We see that this collective balance of social and individual learning seems to be achieved through specialization and selectivity rather than homogeneity in this kind of classic Rogers paradox setting. We see the in degree and out degree and leadership are consistent and related to one another, but there's no overall relationship to reward, right? So you're not necessarily better off being a strong social learner or being a strong individual learner. But we see that leaders have higher instantaneous reward rates, suggesting some level of selectivity based on success. Our modeling results also reflect this, where we see that there's selective influence of successful versus unsuccessful participants. People move towards successful participants, they avoid unsuccessful participants. However, adaptation to the environment seems to be only found in avoidance of unsuccessful participants. They're still moving towards people who are successful, even in the random environments where it doesn't pay off. And we're only just getting started here. We have a couple more models that are planned, and we also want to run some of these agent-based simulations. So I want to thank my collaborators, and I guess open the floor to some questions.
Great. Thanks very much. We have self-organized some questions from maybe Mark still, and Martin, and then Art.
Charlie, great talk.
Hey, Mark.
So in the participants, do they have a top view? I think they did not have a
No,
top
they
view.
don't have a top view.
The models, they also don't assume that there's a top view available.
Good point. So the models essentially are trying to predict which block will be destroyed, right? So essentially every block has some probability of being selected, right? But these models, in terms of using social information, right, use the visibility data. So we're using this transcribed visibility data to determine which players are visible, which players were observed as being successful or not. So there could be a player behind you finding rewards, but that's not going to factor into your these social features because you didn't observe them, right? So in this sense, we're using the visual fields.
One question is, how would all these strategies change if you did have a top view? Just as in many information environments, right? You're not limited by physical constraints. You just get information from any source, regardless of the physical location of it, right? So does this increase learning? Does it increase confusion? What happens?
The reason that we really wanted to set up this limited field of view, and it's not this top-down perspective, is that it really creates concrete trade-offs between individual and social learning. Right, where if you see this from the top down, nothing in your behavior can really tease apart whether you're using you're doing individual learning versus social learning. And so in this sense, we have kind of a naturalistic trade-off between the two. It's not perfect. There's times where you can also see other people while you're also searching, but there are times where that trade-off is costly, right? As we're seeing that people who attend more to the people are destroying fewer blocks, right? So you're right that it would look quite different from above, but we really want to tease apart the decision to either do individual learning or social learning. But sometimes we kind of do a combination of both together. We also do this in this task, but by having this first person perspective, we kind of get a bit more of a trade-off between these two strategies.
Thanks.
Great talk, Charlie. That was super cool work. So one thing I was thinking about during your talk was what kind of strategies or why people are attending to other folks. And at least in the smooth environments, it seems like there could be a few different possibilities, right? It could be that, attending to a few different people is just a way to they're like extensions of you, and that it just allows you to kind of see a few different, a few additional blocks revealed on any given from moment to moment. It could be that you're kind of using people as cues to where pockets of reward might be in the smooth environments.
I think that latter one.
Sorry, go ahead.
That latter one is kind of what we intended, right? In this,
yeah, cool.
You can use social information as cues. I should mention that this rewards prediction feature includes rewards that you observe other people destroy. So this is not only restricted to individual rewards. So actually, maybe it's a bit of a misnomer that we call this individual. But you're still, even counting for the rewards you observed, we're still moving towards a successful player. We're still seeing reliable influence successful players as well. We're still moving towards them. And so that's kind of a purely social cue that's separate from reward.
Mm-hmm. Cool. Yeah. So one thing I was thinking about, maybe inspired by the first talk too, is, what if rather than, other humans participating in this task, you sort of contrasted that with, these sort of bots or agents that were wandering out into the field and, sort of manipulated how much people knew about, which are bots and what the bots are doing. That seems like it could be sort of an interesting way to get at, why people might attend to different agents that are out there in the field in these group settings. That's sort of my question.
Yeah, great. So I think it's certainly doable. There's been various reinforcement learning frameworks for Minecraft, so we can program a reinforcement learning agent. There's a bit of a control problem, right? In the sense we have to train a rather sophisticated RL agent to control the player to a decent level. And then somehow also kind of perform our tasks, right? So that seems like a lot of engineering for us, and this is already a project that's been in progress for many years now, and I hope to kind of finish this soon. So I think maybe that's kind of the next step. Yeah. Thank you.
I think even, yeah, cool, super, that makes a ton of sense. I think even like a set of random bots or something like that would be sort of an interesting baseline in a way, right? Because that could help isolate, the degree to which the agent is someone who's pursuing a strategy versus something that is just, that you either know or don't know is just randomly crushing
I think
things in
those
the
random
field.
bots would be very random because the degrees of freedom and control in this task are very high. Like you have the WASD keys to move around, and then you have every possible degree of freedom for your mouse movement, right? So they would just be spinning around circles, I think, and fail to destroy any blocks unless we properly train them to be RL agents. And then there's kind of some issues with what objective do you train them on, right?
Gotcha, I understand. Yeah.
Yeah.
I'm also interested in Art's question, so I'll ask mine really quickly. I pay attention to the social norms literature, and in that literature, you oftentimes can't see the success of other players. So I'm just kind of curious whether you've tried situations where people are foraging and they don't get to see other players' explosions of blue puffs. So if you only see the players and not whether they're being successful or not.
Yeah, that's a really good point, actually. We were considering this for a really long time when we were kind of tweaking the experiment, if that was one of the tweaks we wanted to make. But then, yeah, so I think there's too many free variables, right? In the sense of like, it's hard to, in this task is a bit kind of not so, it's hard to tell like if you should copy other people at all, right? So I think if you had no blue puffs, people would just avoid each other, essentially behave like the random environments thing at all times, right? But it's an empirical question. I think at this point, we wanted to make social reward visible to kind of incentivize social learning. Whereas we were a bit afraid that without any of these blue puffs, people wouldn't know how to use social information. Yeah, but it's certainly very interesting. We had considered that kind of design at one point.
It's cool anyway, but I appreciate it. Thanks.
I just had one clarification question. You contrast random versus smooth, and I don't know whether I understand what smooth, the scope of smooth. And is there any other kind of environment that you've considered?
Right.
What's the landscape of environments? Yeah.
Right. So these are generated, and they're using the same Gaussian process model that I described later in the modeling part. But essentially, we have these kind of reward clusters, right? So we first generate a function, a 2D function. So mapping any location on the grid to some continuous value with the Gaussian statistics, and then we essentially set a cutoff, right? So everything above a certain value is a reward, and there's the same probability, a baseline probability of reward in both smooth and random. It's just these ones tend to be clustered together, right? So some of my other work has really looked at how people in either natural environments or these generative environments use the structure to search. Here we're kind of bracketing that out for the time being. We essentially use this model as kind of like that part of the reward learning is kind of more or less an ideal observer. But it seems to work quite well in these settings where we don't fix the parameters of that model like we do here. So it seems already to be a good baseline for how people generalize about structural rewards.
Okay, thank you.
Okay, I think we can begin to segue to our general discussion. So there's only 3 questions on our general discussion so far. So I think we can go through them. Ying, would you like to start with your question?
Sure. Can you hear me okay? Hello?
Yes.
Oh, okay. Thank you. Thank you so much for the presentation. Both are very super interesting. I think my question is for Charlie, and thanks again for your presentation, even you're not, well, very, yeah, in a perfect, wealthy condition. So my question is more about, in a social environment, some people tend to always observing what other people doing, and some people just pretty much, it doesn't matter what other people do, I'm gonna do what I do. So my question is more broad, probably not necessarily in your experimental condition, is any insights about how would you incorporate expertise and all confidence? They're not necessarily the same thing, but any insights would be really interesting to know.
Right, that's a
if
very
you're
good point. So we actually one analysis I haven't done yet is that we also ask people for kind of for information about their experience playing like first-person video games, just to get some baseline of like how familiar they are with this. And so I think one analysis I'm meaning to do is also just relate that to the leadership or in a degree. And I'm sure there's going to be some relationship there, right? But what's interesting is that these kind of expert people, via the kind of the equalization of social learning, they're not performing better, right? These people who are doing a lot of individual learning, who are being leaders, they're not performing better because the whole Rogers paradox dimensions, right? The second you're finding a lot of rewards, a bunch of people are going to copy you, then it's going to kind of more or less even out, right? So we have a really robust balance, but nevertheless, in instantaneous moments, right, we still see selectivity based on success. And with some of the other models we want to do, we also hope that are curious to see if we'll see selectivity based on strategy as well, right? And I think that would be very interesting.
A very quick point, because this is the modeling and big data kind of abstract and predicting. I'm just curious because we do a lot of experiment. My curiosity is about the personality tied to their way of performing, like in human resources, the big five personality, the openness, like the introvert, extrovert. So I'm more thinking about before they play the game, do a quick big five personality check, and you can either use the control or.
No, that's a good point. So I'm not really a personality psychologist, and this wasn't something that we had done. So it's kind of the window of time somewhat passed now for that. But I think there definitely is going to be something interesting. These seem like they're stable traits in terms of the social learning strategies. And I think it'd be very interesting to connect this to personality traits, although I don't have a good prediction about which of the big five dimensions will map onto this. But I think it's very interesting.
Quick thought. Thank you so much.
I do have gender though, and I think Art's results showing that females are much better at this kind of collaborative decision making. Maybe gender could also be something interesting to connect to some of these variables. I haven't thought of that yet.
Yeah, great. Thank you so much. Yeah, gender is interesting. Thanks.
Okay, so I think I was responsible for the first question, so I'll give a little bit of context for it, and maybe thinking about like basketball performances, maybe how I'd introduce it. So there used to be a time when like basketball players were assessed on how many rebounds they got, how many points they got. And then there was this sport metric change where they began to look at how many points the team got when a particular player was on the court. And then there was some elaborations of that to look at what pairs of players were particularly useful, scored a lot of points when they were on the court at the same time. And so I think this kind of question comes up most obviously for Art's talk, but I think there's also a relevance for Charley's talk. And so to what extent should we be trying to assess the individual versus really putting our emphasis on the performance of the entire team, and how would that change our assessment vehicles? And in the context of Charley's question, it has to do with like what is moves that the group makes so that they end up with a good balance between, for example, the celebrities and the paparazzis.
So let me start out answering that question. The impact on the teamhood influencing the individual versus individuals influencing team was one highly discussed in there. And of course, we had individual problem solvers, individuals with agents, so we really couldn't assess that. However, Nia Dowell's work had an interesting question, namely the composition of male versus females in a team of four. Sometimes there's one female, sometimes zero, sometimes two or three. And she found that the problem-solving performance of the group was superior, slight edge is higher if you have at least one female in there. Interestingly, it didn't matter whether there were 2 or 3, but at least one female seemed to raise it. And that's where an individual characteristic can influence the group. The one other thing, one of the databases she did was Jamie Pennebaker's database, where you have one individual that is part of like 8 different groups with different compositions. So you can look at the individual in these different contexts. He also gave the big 5 personality tests on that. So Jamie Pennebaker has a golden set of data that can be analyzed by people to look at that very question. Yeah.
And I think to follow up, I think my behavioral data, we can't statistically answer this, but with those agent-based simulations, we can kind of create different groups with different compositions of models, and essentially that might be able to tell us, okay, what characteristics of the group, what type of group compositions perform best objectively, and I guess that second question of how an individual might change the group if we kind of tweak one individual to have different parameters.
Great. So there are a lot of questions on the vote. So while we're here, could I ask the person who asked the question about expertise to ask the question?
I think it was Ian who.
Oh, okay. I think
did.
the feasibility of studying human collaboration question.
Yeah.
And then I'll look at the chat beyond that.
Let me turn off my phone here. Human collaboration is being explored with the Educational Testing Services Group with their EPCAL system, where they're collecting with 2 to 4 people in a group, and where you get to see their face, and they have a goal and do collaborative problem solving, and every chat message is tracked, every action is tracked, and they're right in the middle of doing that human collaboration in fine detail. It'll be interesting to see what they discover. Pat Killinan is at Educational Testing Services, the person to contact on the progress of that research. But right now, it's really an exploratory study where they're trying to look at strategies and patterns and eventually thinking about assessment. So at some point when you can have humans interacting with each other, you can have an assessment without the agents. But one problem is there's an issue of time. There are some conditions that you want to assess that rarely occur. So you'd have to wait for hours or months before you have that situation with a human-human interaction. And people tend to be overly polite. There's not enough discord and things like that. So, but still, people are exploring that. And of course, people at the conference, computer-supported collaborative learning, they have a number of people who try to do just that sort of thing.
I've also got a collaboration where I'm trying to study human-human collaboration on really large scales. So this is a project led by Natalia Velez. And we're analyzing data from this online game called 1 Hour, 1 Life. So it's a persistent world. People live a whole life in 1 hour. So they're born to another person who's already online, and they're dependent on them to take care of them until they're an adult after like 14 minutes. And then they interact with the world, build technologies. And we're looking at these really interesting collaborations in terms of like, how do people collectively assort themselves into different division of labor type jobs, different roles, right? So we can look at the giant interaction patterns of this data set and I used non-negative Bayesian factorization to kind of learn these latent job embeddings for different individuals. We see how people sort themselves into either this role being a baker or a carpenter. And we're also able to model things like social transmission of knowledge, where interacting with people who have this underlying skill set can also influence you in these skills. So this is a way where we have this kind of really naturalistic data. Of course, people are not restricted to their life in the actual game, but they live multiple lives. So we can control for this statistically. And we have really rich data in terms of how these people are interacting with one another, building developing new inventions and innovations, and setting up large-scale projects like farming, which requires multiple individuals over multiple lifetimes to collaborate and develop. So that's one way it's possible with just to study this in kind of naturalistic context.
Barbara, you're up. Gabriella, you're on deck. But Barbara is muted. So let's do Gabriella and.
I'm unmuted, sorry.
Okay.
The interfaces. I'm on an iPhone. So I'm resonating to the basketball example and to Art's comments on waiting for things to happen. I am worried that these situations take out the juice. What's really happening in face-to-face interactions, or even certain mediated ones where you can see people's faces, their hands, and in particular having a joint space that they can think with collaboratively. So basketball is second by second interaction. It's reading bodies for intentions. It's understanding your teammates, your opposition. It's all changing rapidly. So, and yet star basketball players and even not so good ones are able to use that information to collaborate effectively. So we did a small study, and others have done similar things, where we took pairs of people and their job was to find a route, this is Stanford, after an earthquake to rescue as many people as possible. So it's a route on a map. We had dyads that were separated by a shower curtain, so they couldn't look at the same map. They each had a map, but their interaction was only verbal. We had, but it was almost it was essentially unmediated. They just didn't share a common workspace. We had dyads that were working together over the same map. The spatial distance was the same. The conversation was gestures on the map. The words just elaborated that. They were looking at each other's fingers on this shared workspace. The people who could do that found better solutions and were happier with the collaboration. They also collaborated more. They were working on tasks together, whereas the group separated by a shower curtain were often working on independent tasks. So again, I think a shared workspace, watching each other's faces, and even more their hands, their gestures, are critical to any kind of effective collaboration. And I worry that some of these ways of studying are leaving out those essential components to collaboration. Thank you.
Well, one thing I'd like to say in here, and this is particularly the data with the EPCAL project at ETS, they have chat, they do have shared activity spaces, and they have face. You get to see the face, you get to see the speech, very multimedia. So it would be interesting to see make those comparisons that you speak of. Um, of course, it's not there in flesh and blood, but you know, it's a reasonable facsimile, and you know, people like Zoom here. What we miss here in Zoom is we don't have a shared activity space. We're missing that. And so, but maybe we will have such a space in the future.
But we're not collaborating to solve a problem. So,
True.
right. Okay,
Yeah.
I'll try to be quiet now.
Well, we do have the Jamboard. I just pulled it up now. This is in the chat. My Minecraft experiment actually originally started as a VR experiment, and it's actually fully playable in VR. We also collected some VR data, but the issue is locomotion. Realistic locomotion over those large spaces is just not possible. Rather, people use teleportation as the best method, and then we just lose these realistic spatial trajectories, right? We found out that actually with the mouse and computer that the gaze trajectories were not that different with VR, but we're losing out on the space trajectories. I guess in the VR world, you actually see each other's hand movements and you have more nuanced head tilts information. So in that sense, you're kind of interacting almost like in a basketball type setting where you can see people's movements in a more nuanced way. But I think for depending on what type of task you're interested in is not always important, right?
Okay, finally, Gabriela.
Hi, thank you. I've been enjoying both of these presentations, and I immediately, Charlie, when you started talking, started thinking about that Scrub J experiment from way back in psychology on episodic memory. And so part of me thinks of Scrub Jays as these individuals, but then the video gaming part of me is very interested in the comparison between social cognition and social learning in these particular environments. And if you're looking at that, or if there are ways that you might be looking at that, because in my experience, you have so many types of people in the video game environment. And the moment you put them in that sandbox, sometimes the displays and the inhibitions and the disinhibitions and all the things that can creep up. But with social cognition and social learning, there is some tension there between them because they're kind of nuanced. And I was just curious to see if you had looked at any of that.
Could you clarify what the distinction is for you between social cognition and social learning? Because I feel like they're quite related.
Okay, so for me, social cognition is that process where people are remembering and using the information they gather in social context to sort of explain the behaviors that they're seeing or to predict the behaviors that other people are going to engage in. And I look at this purely from a gaming perspective as a person who's been in guilds and things of that nature. And so when someone is new to that particular community, the social cognition, you can really see it. They're trying to get the lay of the land, and how they learn to play the game is through what they see, and not necessarily imitate, but the social fabric that's going on around them helps to inform the decisions that they make. Whereas social learning is sometimes like more of that imitation of behaviors that you would see. So it's observing and learning by that, but the social cognition is a little bit more, you know, prediction versus imitation.
Right. So I think there's certainly much more than just imitation in terms of social learning. And some of my work is trying to look at models of theory of mind, how we're doing kind of this inference about the hidden mental states to predict people's behavior. But I guess within this task, there's too many degrees of freedom to really do that kind of inference in a tractable way, right? We can't really develop models to the theory of mind in this really rich context very well. And in the experiment, as opposed to kind of more sandbox style online environments, we kind of set up the norms as much as possible in the tasks, right? We had that tutorial round, but then we also have a couple training rounds before they actually start the task. And there's quite clear instructions for how to kind of figure out how the game works, as opposed to these kind of normal online environments where you have a lot of exploration and learning from other people about how the task works. We have quite clear instructions, right? So we try to minimize that, but there's clearly, you're right, there's clearly a lot of that aspect to social cognition, and it's certainly something I'm also very interested in.
Thank you for that. And as an aside, sort of what just happened today is a great example of social cognition. In our previous meetings, we have been just raising our hands to ask questions. And today we were given a different set of instructions. And so after people observed and predicted how others were going to do this, then we started all kind of falling in line in a way. So that helps, if hopefully, to give us a real life applicable example we just participated in.
I think we still have to work out some of the kinks on the technology there, lest we suffer too much techno stress, as Kylie put it. But thanks both to Art and Charley for stimulating conversations. And we hope to see you next week, where Mirta Galisic, one of the co-organizers for this conference, and Stephen Lewandowski will be talking. Okay, thanks very much.
Thanks so much, folks. Yeah, bye-bye.
Thank you. Bye.